interval arithmetic, interval mathematics, interval analysis, or interval computation, is a method developed by mathematicians since the 1950s and 1960s, as an approach to putting bounds on rounding errors and measurement errors in mathematical computation and thus developing numerical methods that yield reliable results. Very simply put, it represents each value as a range of possibilities. For example, instead of estimating the height of someone using standard arithmetic is 2.0 meters, using interval arithmetic we might be certain that that person is somewhere between 1.97 and 2.03 meters. This concept is suitable for a variety of purposes. The most common use is to keep track of and handle rounding errors directly during the calculation, and of uncertainties in the knowledge of the exact values of physical and technical parameters. The latter often arise from measurement errors, and tolerances for components are due to limits on computational accuracy. Interval arithmetic also helps find reliable and guaranteed solutions to equations and optimization problems. Mathematically, instead of working with an uncertain real x, x, we work with the two ends of the interval a, b, a, b, closing curly bracket, that contains x, x. In interval arithmetic, any variable x, x, lies between a, and b, b, or could be one of them. A function f, when applied to x, x, is also uncertain. In interval arithmetic, f, produces an interval c, d, c, d, closing curly bracket, that is all the possible values for f, x, x, closing curly bracket, for all x, a, b, x in a, b, closing curly bracket. Introduction. The main focus of interval arithmetic is the simplest way to calculate upper and lower endpoints for the range of values of a function in one or more variables. These endpoints are not necessarily the supremum or infimum, since the precise calculation of those values can be difficult or impossible. Treatment is typically limited to real intervals, so quantities of form a, b, equals, opening curly bracket, x, r, pipe, a, x, b, closing curly bracket, display style, a, b, equals, x, in, mathbar, r, pipe backslash, a, leq x, leq b, closing curly bracket, where, a, equals, minus, infinity, display style a equals, inf d, and, b, equals, infinity, display style b equals, inf d, are allowed. With one of them infinite we would have an unbounded interval, while with both infinite we would have the extended real number line. As with traditional calculations with real numbers, simple arithmetic operations and functions on elementary intervals must first be defined. More complicated functions can be calculated from these basic elements. Example. Take as an example the calculation of body mass index, BMI. The BMI is the body weight in kilograms divided by the square of height in meters. A bathroom scale may have a resolution of 1 kilogram. We do not know intermediate values, about 79.6 kilograms or 80.3 kilograms, but information rounded to the nearest whole number. It is unlikely that when the scale reads 80 kilograms, someone really weighs exactly 80.0 kilograms. In normal rounding to the nearest value, the scales showing 80 kilograms indicates a weight between 79.5 kilograms and 80.5 kilograms. The relevant range is that of all real numbers that are greater than or equal to 79.5. while less than or equal to 80.5. Or in other words, the interval 79.580.5. For a man who weighs 80 kilograms and is 1.80 meters tall, the BMI is about 24.7. With a weight of 79.5 kilograms and the same height, the value is 24.5, while 80.5 kilograms gives almost 24.9. So the actual BMI is in the range 24.524.9. The error in this case does not affect the conclusion, normal weight. But this is not always the position. For example, weight fluctuates in the course of a day so that the BMI can vary between 24, normal weight, and 25, overweight. Without detailed analysis, it is not possible to always exclude questions as to whether an error ultimately is large enough to have significant influence. Interval arithmetic states the range of possible outcomes explicitly. Simply put, results are no longer stated as numbers, but as intervals that represent imprecise values. The size of the intervals is similar to error bars to a metric in expressing the extent of uncertainty. Simple arithmetic operations, such as basic arithmetic and trigonometric functions, enable the calculation of outer limits of intervals. Simple arithmetic. Returning to the earlier BMI example, in determining the body mass index, height and body weight both affect the result. For height, measurements are usually in round centimeters. A recorded measurement of 1.80 meters actually means a height somewhere between 1.795 m and 1.805 meters. This uncertainty must be combined with the fluctuation range in weight between 79.5 kilograms and 80.5 kilograms. The BMI is defined as the weight in kilograms divided by the square of height in meter, using either 79.5 kilograms and 1.795 meters or 80.5 kilograms and 1.805 meters gives approximately 24.7. But the person in question may only be 1.795 meters tall, with a weight of 80.5 kilograms, or 1.805 meters and 79.5 kilograms. All combinations of all possible intermediate values must be considered. Using the interval arithmetic methods described below, the BMI lies in the interval 79.585 / 1, 795, 1, 805, 2, equals 24, 4, 25, 0. Display style 79.585 / 1, 795, 1, 805, caret 2 equals 24, 4, 25, 0. Closing curly bracket. An operation O P. Display style Langle. Math room op. Wrangle, such as addition or multiplication, on two intervals is defined by x1, x2, O P, y1, y2, equals, opening curly bracket, x, O P, y, pipe, x, x1, x2, and y, y1, y2, closing curly bracket. Display style x_1, x_2, opening curly bracket backslash, Langle, math room op, wrangle, closing curly bracket, y_1, y_2, equals x, Langle, math room op, wrangle, y, pipe backslash, x in, x_1, x_2, backslash, mbox, and y in, y_1, y_2, backslash closing curly bracket. For the four basic arithmetic operations, this can become x1, 2, O, P, Y, 1, Y, 2, equals, min, X, 1, O, P, Y, 1, X, 1, O, P, Y, 2, X, 2, O, P, Y, 1, X, 2, O, P, Y, 2, max, X, 1, O, P, Y, 1, X, 1, O, P, Y, 2, X, 2, O, P, Y, 1, X, 2, O, P, Y, 2. Display style, begin, aligned, X underscore 1, X underscore 2, backslash, Langle, mathroom, op, wrangle, Y underscore 1, Y underscore 2, and equals, left, min, X underscore 1, Langle, mathroom, op, wrangle, Y underscore 1, X underscore 1, Langle, mathroom, op, wrangle Y underscore 2, X underscore 2, Langle, mathroom, op, wrangle Y underscore 1, X underscore 2, Langle, mathroom, op, wrangle Y underscore 2, right, and qquad, left, backslash, max, X underscore 1, Langle, mathroom, op, wrangle Y underscore 1, X underscore 1, Langle, mathroom, op, wrangle Y underscore 2, X underscore 2, Langle, mathroom, op, wrangle Y underscore 1, X underscore 2, Langle, mathroom, op, wrangle Y underscore 2, right, backslash, mathroom, end, aligned, provided that, X, O, P, Y, display style X, Langle, mathroom, op, wrangle, Y, is allowed for all, X, X, 1, X, 2, display style X in, X underscore 1, X underscore 2, closing curly bracket, and, Y, Y, 1, Y, 2, display style Y in, Y underscore 1, Y underscore 2, closing curly bracket. For practical applications this can be simplified further. Addition, X, 1, X, 2, plus, Y, 1, Y, 2, equals, X, 1, plus, Y, 1, X, 2, plus, Y, 2, display style, X underscore 1, X underscore 2, plus, Y underscore 1, Y underscore 2, equals, X underscore 1, plus Y underscore 1, X underscore 2, plus Y underscore 2, closing curly bracket, subtraction, X, 1, X, 2, minus, Y, 1, Y, 2, equals, X, 1, minus, Y, 2, X, 2, minus, Y, 1, display style, X underscore 1, X underscore 2, dash, Y underscore 1, Y underscore 2, equals, X underscore 1, Y underscore 2, X underscore 2, Y underscore 1, closing curly bracket, multiplication, X, 1, X, 2, Y, 1, Y, 2, equals, min, X, 1, Y, 1, X, 1, Y, 2, X, 2, Y, 1, X, 2, Y, 2, max, X, 1, Y, 1, X, 1, Y, 2, X, 2, Y, 1, X, 2, Y, 2, display style, X underscore 1, X underscore 2, CDOT, Y underscore 1, Y underscore 2, equals, min, X underscore 1, Y underscore 1, X underscore 1, Y underscore 2, X underscore 2, Y underscore 1, X underscore 2, Y underscore 2, max, x underscore 1, y underscore 1, x underscore 1, y underscore 2, x underscore 2, y underscore 1, x underscore 2, y underscore 2, closing curly bracket, division, x 1, x 2, slash, y 1, y 2, equals, x 1, x 2, 1, slash, y 1, y 2, display style, x underscore 1, x underscore 2, slash, y underscore 1, y underscore 2, equals, x underscore 1, x underscore 2, cdot, 1, y underscore 1, y underscore 2, closing curly bracket, where, 1, slash, y 1, y 2, equals, 1, slash, y 2, 1, slash, y 1, display style 1, y underscore 1, y underscore 2, equals, 1, y underscore 2, 1, y underscore 1, closing curly bracket, if 0, y 1, y 2, display style 0, noten, y underscore 1, y underscore 2, closing curly bracket, for division by an interval including 0. First define, 1, slash, y 1, 0, equals, minus, infinity, 1, slash, y 1, display style 1, y underscore 1, 0, equals, unfd, 1, y underscore 1, closing curly bracket, and, 1, slash, 0, y 2, equals, 1, slash, y 2, infinity, display style 1, 0, y underscore 2, equals, 1, y underscore 2, unfd, closing curly bracket, 4, y 1, less than, 0, less than, y 2, display style y underscore 1, less than 0, less than y underscore 2, we get, 1, slash, y 1, y 2, equals, minus, infinity, 1, slash, y 1, 1, slash, y 2, infinity, display style 1, y underscore 1, y underscore 2, equals, unfd, 1, y underscore 1, cup, 1, y underscore 2, unfd, closing curly bracket, which as a single interval gives, 1, slash, y 1, y 2, equals, minus, infinity, infinity, display style 1, y underscore 1, y underscore 2, equals, unfd, unfd, closing curly bracket. This loses useful information about 1, slash, y 1, 1, slash, y 2, display style 1, y underscore 1, 1, y underscore 2, closing curly bracket. So typically it is common to work with minus, infinity, 1, slash, y 1, display style, unfd, 1, y underscore 1, closing curly bracket, and 1, slash, y 2, infinity, display style, 1, y underscore 2, unfd, closing curly bracket, as separate intervals. Because several such divisions may occur in an interval arithmetic calculation, it is sometimes useful to do the calculation with so-called multi-intervals of the form I equals 1 L x I 1 x I 2. Display style text style big cup underscore I equals 1 caret L x underscore I 1 x underscore I 2. Closing curly bracket. The corresponding multi-interval arithmetic maintains a disjoint set of intervals and also provides for overlapping intervals to unite. Since a real number r display style r in mathbar r can be interpreted as the interval r display style r closing curly bracket. Intervals and real numbers can be freely and easily combined. With the help of these definitions, it is already possible to calculate the range of simple functions, such as f a b x equals a x plus b, display style f a b x equals a c dot x plus b. If, for example, a equals 1, 2, display style a equals 12, closing curly bracket, b equals 5, 7, display style b equals 57, closing curly bracket, and x equals 2, 3, display style x equals 23, closing curly bracket, it is clear f a b x equals 1, 2, 2, 3, plus 5, 7, equals 1, 2, 2, 3, plus 5, 7, equals 7, 13, display style f a b x equals 12, c dot 23, plus 57, equals 1, c dot 22, c dot 3, plus 57, equals 713, closing curly bracket. Interpreting this as a function f a b x, display style f a b x, closing curly bracket, of the variable x, display style x, with interval parameters a, display style a, and b, display style b, then it is possible to find the roots of this function. It is then f 1, 2, 5, 7, x equals 1, 2, x plus 5, 7 equals